recording. So I just wanted to remind you that you should be working on those portfolios. You're going to have plenty of time, which is why I try to get the content done early. So you have a little stretch period where you can finish up your work in Alex and work on those portfolios. Does anybody have any questions or concerns they want to throw out there for me? I mean, we are getting pretty close to the finish line here, because once I finish this chapter and you test, we only have 2 or 3 sections left. And that's going to happen very quickly. That's in chapter 4. We don't officially test in chapter 4, but those topics will be on the final. The final will be in Alex, and you'll be monitored using a professional system called Honor Lock, where there will actually be a live person watching you. You'll have to present your ID at the beginning of the session, give a 360-degree view of your room. They'll ask you to, turn the computer completely around and have your workstation, wherever you're going to take the test, completely visible so they can see how many sheets of paper. I will let them know that you can have 4 cards, 1 for each chapter with your formulas on it. They have to be 3x5 note cards, no bigger than that. And that, of course, you can have your calculator. As always, on this upcoming test, I don't know that I need to say this, but I'm going to post it as an announcement. Every test is taken in the same manner. You will get a grade in Alex, and that grade will remain as is unless you don't turn in your work. Okay, and let me talk about what some people have done. Showing your work does not mean that out of 25 problems you show 3 problems of work. I also cannot give you credit for your work if you don't number them, because then I can't tell which ones you're showing work for and which ones you're not doing work for. So there is a big portion of this when it comes to showing work that is your responsibility. It needs to be numbered, legible, and in order. And that is what you're supposed to submit to me. If you submit no work at all, your grade automatically gets cut in half. If you submit a subpar amount of work, meaning here's everybody handing in work for 20 of the 25 problems, and here you come only giving work for 3 problems, that's not adequate. Then your grade will go down by a certain percentage. So don't let that happen to you, because the tests are meant, they're not going to be like overly hard if you've been attending class and doing the homework, and you've seen, especially if you've been coming to class, because then you've been exposed to the Alex and the book. So if you have any questions about that, I just want to reiterate, I put it on the announcement board because some people thought that test 2 was taken in a different manner than test 1 and didn't turn their work in, but that was very few people. Okay, so let's move on to the material. Stop me at any time that you would like to ask a question, and I'll be happy to try and explain it in a different way. When we get to section 3.10, which is the last section in that chapter, but we're going to go back to section 3.7 after this because I need to cover that as well. You're solving what's called a system, a linear system. Linear means that all the variables, these are variables, x and y, that all the variables are first degree. That's what the word linear means. Linear also means that when you graph this equation, it's a line. When you graph this equation, it's a line. So you're working with 2 lines at one time, only you're being given these lines in equation form. So collectively, this is called a system. Okay, so now what we're going to do is we're going to work on trying to find a solution for this system. So let me tell you what that means. A solution is a point. It's going to be an XY pair, and that's one of the things we're supposed to fill in right here. The solution for a system is an XY pair like this. So in other words, you're going to be giving me 2 numbers, the X and the Y coordinate. What you're really finding, if you want to talk about it graphically, and that will be some of the problems that are going to be thrown at you, where they give you a graph and you tell what the answer is. Those happen to be the easiest form of the particular type of problem we're learning right now. And where the 2 lines hit, right where they hit at a point. They cross at a single point, and that point has an X and a Y coordinate, as all points do in the Cartesian system. So it'll be an XY pair like, like that. You'll have a number here. It could be a fraction, or it could be a negative, whatever. That'll be the numbers at which it hits. Now, there are 3 different levels on which this question is asked. Whenever they're talking about systems, there's what I would consider level 0. That's where they give you a graph and they ask you to just look at it. There literally is no work for that particular type of problem. There's no steps that you could possibly do to get the answer. It is a matter of just looking at the graph and seeing where the 2 lines intersect, where they hit, and naming the numbers. So there is no work, and I understand that there are some problems like that on the test, but the majority of them there's work for. That's why I'm able to show you so much work while giving you these notes. So that is, I'm going to consider that level 0. I consider this the middle type problem. This would be what I would consider level 1 when you're talking about solving a system, where they give you the system. The system is the 2 equations. And then they give you numbers. I know this came out a little bit light. Sorry about that. Certain things don't print well. They give you a point, an XY pair, because as I stated up at the top of the page, all potential solutions come in an XY format. So they give you a pair, and then they just want to know, is this a solution or is it not a solution? So for this to be a solution, it has to work in both equations. Both equations, not just one. If it only works in one but not in the other, then it is not truly a solution. How do you know it's working? When you plug it in, you should get a true statement. So if you don't get truth both times, it's not a solution. So here we go. Let's try it out. Notice that there is an X and a Y variable. Variables are places where you can plug in numbers. And you are given 2 numbers. You're given X is 5 and Y is 4. And we want to know, hey, is that really a point that's on this line? Because this is the equation of a line. So open up a spot to dump in the X. Open up a spot to dump in the Y. And let's see if we get a true statement. And then what I'm doing here, I'm going to do to the other equation also. You must get a true statement both times. So let's see. They said use 5 for X and 4 for Y. And then you can just get your calculator involved if you need to. This is 28. 20 take away 28 is -8. And I have a -8 on the other side. What's considered true when you're plugging into an equation is that you get the same number on both sides. So this is a true statement. Okay, now let's try it in the other one. If it also works here, then we will say, yes, this point containing this X and Y pair is a solution. Okay, let's do the same thing. Open up a spot for X. Open up a spot for Y. And dump in the XY pair, 5 for X, 4 for Y. So here we get 15, and possibly you can see that this is already not working, because over here I get 23, over here I get -6, and of course 23 equals to -6. That's not true, it's false. So when both of them don't come out true, that means nope, this is not a solution. Going to the next problem, and this is also same type of problem, level 1, where you're not asked to come up with these numbers, you're given the numbers and then just being asked to test out whether it's true or false that this is a solution. In the problems that follow, which I will give you 3 examples of, you're going to actually have to come up with these numbers. That would be level 2, a little bit harder than this. Here you're just plugging in. So now we're going to see, using this same equation, is -2, 0 a solution? So Put -2 in for x because whatever is mentioned first is the x coordinate, whatever is mentioned second is the y coordinate. Put a 0 in here. So 4 times -2 is -8. -7 times 0 is 0, and you can either put -0 or +0 because 0 really has no sign. So it really wouldn't matter what you put in front of the 0. -8 take away nothing, or -8 plus nothing is -8. And of course you get a true statement. So far we're good. And if we get truth again, when we go and plug it in here, then we know that it is this -2, 0 is the solution. We already proved to ourselves that the pair above was not a solution. It's not a point that belongs to both of these lines. It belonged to this line, but it didn't belong here. Okay, so let's test it out in this other equation and see what happens. Oops, running off the page. Okay, so let's see, I'm plugging in -2 for x, 0 for y. This is going to be -6. This will be 0. Anything times 0 is 0. -6 plus nothing, -6. And again, I get truth. So because I got a true statement both times, this time we say, yes, -2, 0 is a solution for this system containing these two equations. Okay, so that's what we consider level 1, where someone gives you the numbers and you're just verifying, is it true in both cases that the point lies on the equations, or is it not true in one or both equations? When you get to this kind of problem, then you're at level 3. Oh wait, let's look at the one at the top. I skipped over that. Okay, so there would be a type of problem like this. This I'm going to consider level 0, just because there is 0 work here. There's no work for this problem. Okay, if you understand that the solutions that you're finding are where the two lines hit, there's going to be one solution, if any. Because sometimes it's true that you could graph two lines and they don't intersect, they don't hit, but these do. So instead of doing all the work of plugging in or finding the numbers yourself, you just look at it. There's nothing really to do other than to identify this number. There's no steps to do. It's just, where is this point right here, this intersection point? 1, 3. That's the answer. So the point of intersection represents the solution. The point that you're giving for your solutions is always a point that belongs to both lines. And so we call it the point of intersection. Okay, so no work there. And this would be the hardest type of problem, where you're going to actually come up with both of the numbers yourself. Okay, all of these concern solving a system. Okay, so what I'm going to demonstrate for you, because it is the easiest of the ways that there are for solving a system. I mean, one way is to have a graph where somebody provides a graph for you. I mean, if you were in an algebra class, we would ask you to produce both of those lines yourself and then identify where they hit. So you'd have to do it from start to finish, even creating the lines. But in this class, we will provide the graphs for you, and we would like you to get I would like you to get familiar with the fact that where they hit, right there, is the actual solution. And understand that this is the easiest of the cases. That's one way to solve. There's also a way called the elimination method, but the substitution method is even easier if the equations are presented in a certain way, such as where they have one variable by itself. That makes substitution really easy, so I'm going to show you how to do that. Okay, so you're going to be working both equations at one time, and you're going to substitute one into the other. It doesn't matter whether you substitute the bottom into the top or the top into the bottom. That's up to you. Either one will get you the same answer. When I say you can do it either way, it means you're going to get the same answer either way. So like, for instance, notice that you have two expressions for y. They say x plus 4 is equal to y, and they also say 3x minus 10 is equal to y. So what you want to do is you need to have an equation that doesn't have two different variables, because then you can't solve. If you're going to be able to solve, you need an equation that either has just x or just y. Now, they've made it very easy for you to get rid of the y's, because look what you can do, and this is why it's called substitution. If they're telling you that y is equal to x plus 4, that means you're allowed to put x plus 4 in anywhere that you see a y in either of these equations. Now, you don't want to do, plug this x plus 4 in over here, because then you're going to get 0. You want to work both of these equations at the same time. So you're going to take something from here and substitute it in here, or vice versa. You could take something from here and plug it in there. I'm going to go like this. I'm going to substitute into the bottom equation. I'm going to take x plus 4, which is equal to y, and I'm going to plug it in for y. Thus creating, okay, here I go. I'm going to write the bottom equation, plugging in x plus 4 for y, replacing the y, x plus 4, copying the equal sign, copying the right-hand side. So all I did was take that bottom equation and replace the y with what it's equal to. Y is equal to x plus 4, so says the top equation. And that's what substitution is. You're allowed to replace one thing with another if they're equal. Now what I've created is an equation that only has one variable, and so I'm good to go for solving. So we've been concentrating quite a bit on solving. One of the problems that you were presented in section 3.3, a couple of them was where you had variables on both sides. You need to bring all the variables to one side and then get that variable by itself. You can't have variables on both sides. So you can either bring everything over here or everything over here. That's up to you. If you want to subtract x, let's just say you decide to bring the x's over here. That's fine. Either way will get you the same answer. So if you subtract x here, and again, the reason I'm subtracting x is because this is a positive x. You want to use the reverse, or what we call inverse operation. I'm going to subtract x on both sides. Remember, an equation is balanced on both sides. So whatever you do to the left, you must also do to the right. So this will go away, leaving you with 4 is equal to 3x minus 1x is 2x. And bring down that negative 10. So once you get all the x's on the same side, you don't have to draw that line. I just am in the habit of doing that. Once you get all the x's on either the right or the left, whichever you prefer, then you try to get all the numbers that are hovering around the x, wherever the x is, you try to get those numbers away from the x. You're trying to isolate the x. So first thing I'm going to move, and you will always move anything that's added or subtracted before removing that coefficient. That is very tightly wound to this, so remove it last, or else you're going to create fractions in the middle of the problem. So add 10, add 10. That'll give me, that's gone. Let me bring down my equal sign so I can clearly see my left and my right. This will be 2x. This will be 14. And divide by 2, divide by 2. And I get x equal to 7. I divided because this x was attached to the 2 by multiplication. That's read out loud, 2 times x. Okay, so let's go over these steps. First, I got all x's on one side. These are the specific steps that I did. Step 2, I removed the negative 10 by the addition property. So I added 10 to both sides. This is a 3-step process. And as my third step, I did division. You're always going to do the division. You're going to remove that multiplication. If it's a fraction, you're going to find yourself multiplying by the reciprocal. If it's not a fraction, as this one isn't, you're going to find yourself dividing to get rid of it. and then I divided both sides by 2. So 3 steps. Okay, now let's go back to the main emphasis of this section. You are trying to find where these 2 lines intersect. All points of intersection, just like this one, come in the form of XY pair, where you will state the X as well as the Y. You don't have to put X and Y under there. I'm just trying to be explicit. Notice that all you have is the X so far. You have not yet given us the Y partner, and every X will have a Y partner. So as soon as you find the X, you are now going to substitute into either equation with this value that you presently know, called X equal to 7. You're going to take that and you can plug it either into the top equation or the bottom equation. You're probably going to pick whichever one looks more pleasing to you. Smaller numbers, less negatives, that's what people are drawn toward. Now, if they're both really simple, just pick either one. I'm just going to use the top equation for the heck of it. So I like to write it down first so I can focus. I then want to concentrate on the fact that for one of these variables, I'm going to plug in a number. Which one? X, because that's the one I presently know. So I'm going to put the 7 right there. And finally, I get Y is equal to 11. So now you have a complete pair, and you can give your solution as an XY pair. X is 7, Y is 11. And this is your final answer. So considerably more work than what we did in the first problem, and a lot more work than what we did when we just looked at the answer. You've done everything from start to finish to find these 2 numbers, and that's level 2. Okay, let's try that again. And then I'm going to let you take a shot at it. I'll give you a problem, and then we'll do a poll, and everybody can answer in the class poll. Okay, so here we go. Now again, you can either plug information from this equation in here or information from this equation in here. The reason I gave you this one is because in the last problem, it was easy enough to go with either decision. Here, the best decision is to plug this information into this. You know how you can tell that? You want to look for the equation that has one of the variables isolated, where there's nothing being multiplied, nothing being added or subtracted. So look for the equation, this one right here, that looks like that. See, this doesn't have X by itself. The Y is not by itself. So this one's in better shape for substituting into the top equation. See how it says Y is equal to 2X? That means you can put this 2X in for Y, wherever you see a Y, in the top equation. Very easy to do that substitution, okay? Wherever you see Y, you may plug in 2X only because they are equal, so says this bottom equation. It's going to be X plus Y is equal to 3. I'm copying the top equation, but I'm getting ready to substitute into it. What am I substituting? 2X in place of Y, right in there. 2X in place of Y. And in doing so, you get rid of the variable Y and can now find your first answer. This is 1X plus 2X is 3X. So all I did right now is I collected like terms, just so I only have the X in one place. I don't have the issue in this problem of having X's on both sides, so that's nice. It means I'm going to have less steps, and I can jump right into my final step. There isn't anything being added or subtracted from the x, so that's a step that I had in the previous problem as well. All I have to do is jump into removing this 3 by division. Likewise on the other side. Again, once you get that first value, you only have half of the answer and you must continue with the problem. Okay, so far I have the x and I would like to find the y partner. It is your choice which equation to use. I kind of like that second one, the bottom equation. It's just really simple. It has no plus or minus signs in it, so I'm going to use that to finish this problem. I'm just going to go, okay, I'm going to write down the equation that I have chosen to use, and I'm going to plug into it. Where do I plug in? Y or x? Well, you just found that x is equal to 1. So that means you're allowed to plug in a 1 for x and nowhere else. And you end up getting 2. So now you know that y is 2 and x is 1. So you can give your final answer as 1, 2. Okay, so now what I'm going to do is I'm going to write an equation here. I want you to write it down somewhere. And then we're going to poll for the answer. Hold on for 1 second. Okay, let me write this problem here. See what you can do with this now that we've done a couple of problems. I mean, I want you to try the hardest version because the other problems are going to be pretty easy for you. Let's see what you can do with this so I can see whether I need to do another problem. All right, so one of the equations is going to be 2x plus y. Please copy it down somewhere because when I do the polling question, I'm not going to retype the equations in there. So one of them's 2x plus y is equal to 7. And then the other one below it will be y is equal to, let me move this over a little bit. Y is equal to 4x plus 1. I copy that down somewhere. Try to do it. Let's see what you can do with it. I'm going to say that you've copied that down by now and you're working on it. Here's your question. Okay, so I have 7 responses so far. Let me wait a little longer and give everybody a chance. There's 11 people signed in, so I'm going to wait a little while, a little bit. Okay, it's possible that 2 of our class participants floated off into Never Never Land, so let's go ahead and assume that we have 9 that are actually present. And let's go over this. Okay, so the answer here was no, this is not a solution. The reason is those numbers are not in the correct order. The numbers 5, 1 are not on the 2 lines. It is 1, 5 that's the answer, not 5, 1. So if you could not even begin to get near the answer, I don't know if that was the case of the 2 people that didn't answer or they maybe just floated away. So here it is. Let's go over it real quick. So the best way to go here was to take this 4x plus 1, which many of you did because most of you got it right, and take this and plug it in for y, but in the top equation. So the top equation would have looked like this, 2x. In place of the y that's right there, you put anything that's equal to y, which this says 4x plus 1 is equal to y, so I'm allowed to put it in for y. At that point, I have 6x plus 1 equal to 7 because I collected those terms together. I only have x's on one side, so that's nice. Now I need to start getting everything away from the x. I always start by getting rid of added or subtracted numbers. This is a plus 1, so to make it go away, I have to subtract 1 on both sides. It'll give me 6, while over here I'll have 6x. Dividing that 6 right off of the x, I end up with x equal to 1. And then if I want to finish the problem, I have to pick one of the equations. I like this one because I don't know what y is, and this has y isolated, so it'll be easy to plug into. 4 times x value, I already know the x value, plus 1. Okay, so be careful when you're putting them in order because, Alex will do that also. They'll put them in the wrong order, and if you're not paying attention to what an ordered pair is, you're likely to think something's an answer when it's not. So x is 1, y is 5. The x is always written first. Okay, next question in the polling. Okay, let's take you back. So that's the hardest level. That was level 2. Let me take you back to a level 1 type problem. So instead of you coming up with the numbers this time, which here we did everything from start to finish to find that 1, 5. How about if I give you the 2 numbers and you just try to tell me whether it's a solution or not? So I want to know, is 2, 6 a solution for the following system? One of the equations is 3x plus y equal to 12, and the other equation is y is equal to 2x plus 2. Okay, those are your 2 equations. I want to know if 2, 6 is an answer to that. And then I'm going to put a polling question here, and you can answer either yes or no. Okay, the poll is active. You can answer whenever you're ready. All right, we have 8 people that have answered so far. That's a lot less work than the one that you just did because I gave you the numbers. So this one's just a plug-in. You take the numbers and you just plug them into the 2 existing equations and see if they work. The answer to that, okay, so we got 9 people that answered. Everybody answered yes, so excellent. That was the answer. It did work in both equations. Now, since everybody got it right, I guess you're fine with those. The one that we just did previous to that, I guess, is a little bit harder. So that's pretty much it. Those are the problems on 3 different levels, how you will be asked whether something is a solution to a system. Does anybody have any questions for me regarding how to solve a system? Okay, we are going to backtrack now to section 3.7. That's the only one we have left to cover. Almost everything in that section has to do with what we already learned in section 3. It might have been 3.2, can't remember what it was. I think it was section 3.1 and 3.2, where we were learning how to write the equation of a line. We were learning how to fill out a table and tell whether or not it had a consistent slope, whether the values coming down the side of each column or the same, consistently going down, because then we know that the picture is aligned, that the graph of the equation is aligned. So we're going to get back to more of that, pretty much all the same concepts that were already in your Socrative quiz regarding section 3.2, how to find the slope, how to fill out, number one, how to fill out the table of values for a given equation or a given situation, how to write an equation by finding the slope first and then the formula called the equation of a line using slope and y-intercept. And we went over all of that in 3.2. The only difference in this section is that you'll be in more situations where you're taking a verbal type situation that's explained in sentence form and creating your own equation. The reason that this comes now after section 3.5 is because in 3.5 it was all application problems where you were doing just that. Given a verbal description, a sentence, and then you had to translate it to symbols and inequality symbols and equal signs and that kind of thing. So we're kind of mixing section 3.2 with section 3.5 to come up with what you're going to see in 3.7. Here we go. I'm going to be doing problems in the book because there are no problems in the lessons note packet. So the first one that I want to do is on page 76, if you have your book. And there's a little graphing grid and everything and a table that we can fill out. And let me give you the description of what's going on in this particular table right here. It was on the previous page. I'll just read it to you real quick. Okay, so it says a student organization that you're involved in is planning a year-ending pizza party to celebrate a successful year on campus. As chair of the planning committee, you've wisely worked a deal with the local pizza place to provide large pizza at $9 each. The budget allows at most $175 to cover the food. And of course, you'd like to know how many pizzas you can get while still staying under budget. We'll attack the problem in several different ways. We can use a numerical calculation, and don't forget to write the number of pizzas you can buy. Like if you wanted, they're basically what they're saying in number one is if you wanted to figure this out Bam Bam style and not really get too algebraic, you could just say, okay, first pizza is $9. Let me keep adding 9 until I get as close as I possibly can. 175. I mean, there's a better way to do it, and that would be just to include just a tiny bit of algebra. I mean, just make an equation, and I would suggest this manner in which to figure out how many pizzas you can get. And we're going to do that on the table that's in the next on the next page. We're also going to write an equation for the total cost of the pizzas. We'll do all that on the next page. So all you need to remember from this page is that the person has 175. You can't go over that because once you run out of money, you're not getting any more pizzas. We're going to buy as many as we can. Decimal portions of pizzas don't count. It'll be however many whole pizzas we can get, and they're $9 each. So flipping to the next page, 376 is where the table's been organized, and you had many of these tables in section 3.2. Okay, so if you know that they are $9 a pop, very easy to fill this out. When you buy 0 pizzas, your cost is 0. When you buy 5 pizzas, it would be 5 times 9. I know you can just do that in your calculator, but since you're trying to put up with an annoying teacher that wants you to show their work only because you're going to be asked to do that in all your math classes, then you should plop something out to the side, even though I'm sure you could do it in your head on a calculator. When you get 10 pizzas, it'll be $9 times 10. And I wouldn't even mind if you just did a few and then went off the reservation as far as not showing the rest of them. If I could at least see you setting up a few of them, that would be good enough. And you could do $9 times 15. 1 times 15. And maybe you see a pattern here that it's going up by 45 each time. See, as you go from here to here, 45. Go from here to here, 45. So even without putting this in the calculator, well, unless you need to, 90 plus 45 is 135. Remember we talked about when there's a consistent change each time, plus 45, plus 45, that you are headed into the possibility that what you're graphing is a straight line. If you had another 45 here, you'd be at 170, 180. Sorry, I add in pieces when I'm doing it in my head. If you had another 45 here, you would be at 225. And if you add another 45, you'd be at 260, 260, 270. And you can just use your calculator. Okay, so a table, notice that every time you jump from one number to the next, 45 has been added. So you have a consistent increment of 45 all the way down the Y column. Remember I was discussing in chapter 2 that this column, when you have a table that has vertical columns, the second column will be the Y column and the first column will be the X column. When you have a table that goes horizontally, then the top are the X's and the bottom row is the Y's. So anyway, let's see if we also have a consistent jump as we pass from number to number. Okay, so the first jump is 5. But then when we go from 5 to 10, again, 5. When we go from 10 to 15, again, 5. If the first 3 are the same, it's pretty safe to assume they're all going to be the same. Okay, so the jumps that you're seeing are sometimes very convenient to use when you're going to go and graph. So another thing that you need to be able to do is how to produce a graph from the table to the graph. Now they've already nicely labeled the x-axis for you and they've labeled the y-axis for you. So let's see. Number of pizzas, which is this x column, you have to look at how big the numbers are getting to make sure you have enough grid marks here. Because that'll help you decide, what kind of increments to jump in. Let's see, they're jumping in increments of 5, and if I do the same thing, will I make it to 30? 5, 10, 15, 20, 25 with ease. I could even, make them bigger than that, but it will be super easy to plot the points if you just jump like the table is going. So I'm going to call this, let me just get a better pencil. I'll call that 5, 10, 15, 20, 25, and 30. That way I'll be able to plot each of those x values. See if I can make this a little bit bigger. Maybe. Oh, okay, that's better. And then the numbers in the y column, they go from 0 to 270. 0 to 270. So let's see. And they're jumping in increments of 45. You could jump in increments of 45. You could call this first line right here 45. You can jump just like, this is going to be 0. You can jump just like the table. And it jumps to 135, then it jumps to 180 as far as cost goes. I'm not going to put dollars on each one because the title has it already there. And it jumps to 225. Then it jumps to 270. And there, you made it all the way to 270. Okay, when you go to plot the points, you're plotting ordered pairs that come from the table. Like, for instance, this first couple of numbers is 0, 0. The second pair would be 5, 45. I'll write all the pairs by the graph and then I'll slide up the graph again. Okay, so right from that table, I got all these pairs right here, and I'm just going to plot them. Okay, so you're plotting 0, 0, and you're going to go 5, 45. Sorry if there's noise in the background, but the air show just started in my neighborhood. 1090, we're going to go right here. 15, 135 was the next pair. Notice that they're all lining up in a straight line. And you're going to try and connect them the best you can with a straight line. 2180 goes right there. And it's 25, 225. And then the last one's at 30, 270. And then you just connect them. Make sure you show infinity in one of the directions, because any line actually does go on into infinity, sometimes in both directions, sometimes in just one direction. It's just not a blunt point, it's an arrow. Okay, so that is 2 things that we learned how to do in section 3.2. We completed tables. We learned how to predict what the picture was going to be. Like they'll ask you the question, does this table represent that? Do the values in this table represent a linear graph? They do, because of the consistency of the numbers coming down this side as well as this side. These numbers don't have to match. They just have to be the same going down that specific column and going down this specific column. And then you know ahead of time that the points are all going to line up in a linear fashion. Okay, so we've done that there. We also did things like figure out how slanted the line is. And we learned how to do that both ways. We learned how to find slope using the 2-point formula in section 3.2, like that. And we also learned how to find the slope using rise over run. So if you wanted to know how slanted is this line, you would pick any 2 points you want. I am very into keeping my numbers as small as possible, so I would be very inclined to use that pair of numbers right there, 0, 0, and 545, anything with a 0, and it makes the calculations much easier. So if you were going to do slope, you would just go take the y's, so says the formula, and subtract them on the top. And you can go from here to here or from here to here. But just pick a direction and stick to it. I'm going to go this way. I'm going to start with these numbers and come to the numbers underneath. So my y's would be 0 and 45. The 0 first, and then the 45. I'm going to stick to that direction and use 0 and then 5 for my x's on the bottom. That would give me negative 45 over negative 5, which is equal to 9. So the slope is 9 by the 2-point formula. There was another way that I taught you how to use that to get slope, and that was called rise over run, but we've already done the slope for this one, so I'll do the rise over run method in another problem. Okay, on top of filling out a table, creating a graph from it, finding the slope, all those things were in 3.2, but we also learned how to write an equation that describes the entire line, not just how slanted it is. This just describes what we call the slantedness or steepness of the line. You could say it either way. How steep is that line? But when you want to describe the entire line, including its steepness and including its y-intercept, then you're going to be writing the equation of the line. So we also learned this in 3.2. All of these things will be on the test. That's why I'm reviewing it. And like I said, this section is very much a review of section 3.2. So this was called the slope-intercept formula. And if you don't remember, the m is the slope. That's the variable that all books use for slope. And then this is the y-intercept. Maybe you want to write that somewhere. So you really only have to plug in this number for slope and a certain number for y-intercept, which you are expected to be able to find. So if you wanted to continue this equation, just look for the numbers. We already know that slope is equal to 9, and then the y-intercept is this one right here. Look for the point that has an x value of 0, and then the number right next to it is the y-intercept, which can sometimes also be a 0, but most of the time it's not. So this one is, you just always look for the point where the x value is 0, because that will be the point that's always a point on the y-axis. Whenever x is 0, you see, look right here. This is a point that's on the y-axis, therefore the y value of this point would be considered the y-intercept. This point also serves as an x-intercept because it's on the x-axis as well. So it's kind of like a dual purpose point. Not only is it the y-intercept, it's also the x-intercept. So anyway, the number in that y position is the b value for this equation. So if we wanted to write an equation, I'll continue it over here. It would be y is equal to, what I highlighted are the only things that you plug in for, 9x, and then you put that y-intercept in there. And if you want to give this, a little bit better, you can just call it y is equal to 9x, because 9x plus nothing is 9x. You could give this as your final answer. Okay, so this is the equation of the line. So I've done a lot of descriptions here. Filled out the table, drew the picture that goes with it, did a calculation for how slanted the line is, and then wrote the equation that describes the entire line, including its slope and its y-intercept. And that was over here. Okay, you're doing a lot of the same things in this section. Okay, so now they start to talk at the bottom, and these were some phrases that were used in section 3.5, where we were talking about less than and greater than. Let's drag that into this problem. It says you want to spend at most. When somebody says the most you're allowed to spend is 175, that means you can spend 175 or less. So we were learning to interpret phrases like this. Less than or equal to is what represents the phrase at most. So if you wanted to come up with something that represents the cost of the pizzas in this scenario, you need a variable. How about if we use P for the number of pizzas? Okay, P for the number of pizzas that we're going to be able to buy for this $175. This is just something they were mentioning on the previous page. You need to be able to do things like write an inequality to represent certain stipulations in the problem. And here's the stipulation. That the most you can spend, it is stipulated that the most you can spend is $175. So first you need an expression that represents the cost of the pizzas. Okay, so the cost of the pizzas would be how many pizzas you're buying times $9 each. That's the cost of the pizzas. You don't have to put the dollar sign while we're writing equations or inequalities. So the cost of the pizzas, what you spend on pizzas, if the most you're allowed to spend is 175, can be less than or equal to 175. So if somebody says to you, well, how many pizzas are you actually going to be able to order from this business owner? That means you have to solve it. What is the most number of pizzas you can get for this money under this condition that you can only spend at most $175? Well, you can think of this as an equation. You're trying to isolate the P. Therefore, let me move this over here so I could actually have some room to solve it. If all you want to do is get rid of that multiplier, you get rid of it through multiplication. Oops, I lost my little equal sign. So the number of pizzas, that's what P stands for, that you can buy has to be less than or equal to, let's see what 175 divided by 9 is. Okay, so we get 19.4 pizzas. But if you're going to order pizzas, you don't tell somebody on the phone, hey, I need 19.4 pizzas. The most you can buy is 19 pizzas. They're not selling partial pizzas at this place. And that would be the answer to that problem. You have to stay under 19.4. Okay, any questions on what I've done on this page? All right, so a nice little review there. Okay, so let's look at this problem now. We're going to look at page 377. Okay, so in this particular problem, what they're adding into the scenario here is a $10 delivery charge. I mean, the first ordered pair is not going to make sense to you because you're thinking, if I ordered no pizzas, why am I paying a delivery charge? That kind of doesn't make sense. But they want you to start with 0, 10, and then work up from there. So you're being charged $10 just as a flat delivery fee. Then as far as going to 5 pizzas, the pizzas still cost $9 each, and the most that you're allowed to spend is $175. So you still have a lot of the same stipulations you had in the previous problem. It's just that now this is a place, as many places are doing now when you order food, they're upping that delivery charge. So at 0 pizzas, we're going to spend $10. And then once you start actually ordering pizzas, you're going to pay the delivery charge plus the price of the pizza. So this would be the $10 plus $9 times however many pizzas you're going to order. This one right here will be $10 plus $9 times however many pizzas. Why don't we just put this blank spot for pizzas rather than a P, and we can go ahead and plug these numbers in. So let's see, I'm doing 5 pizzas here. Here I'm doing 10 pizzas just to show you the work, and I would want you to show me the work also. Delivery fee plus $9 times however many pizzas you're ordering, and in this situation I'm ordering 15, and so on. So you get all the way down here, which would be $10 delivery plus $9 times 30. Okay, let's pop those in our calculator. So, and basically you could work off the table that you just made. You just got all of these answers, but without the $10 fee. Like for instance, that first one when you were ordering 5 pizzas was $45. Just add 10 and it's $55. Or you could just put it in your calculator if you want. This is 90 plus 10, 100. This is 9 times 15. That was the 135 plus 10, 145. And the next answer after that was 9 times 20 pizzas, which was the 180 plus 10, which is 190. Then the next one was 25, 9 times 25. I did 9 times 15, 9 times 20, 9 times 25, which is the 225 plus the 10 is 235. And then this last one, 9 times 30 is 270. 270 plus 10, 280. Okay, and same thing. You would plot those going from 5 to 30. So this is going to be 0, 5, 10, 15, 20, 25, 30. And the numbers going up the side is the cost. So it's going to be, now let's see, now these are jumping in increments of $45. But these have to be evenly spaced apart. So I can't label this as, sometimes you can just use the numbers that are right here in the table. But I can't call this 10 and then call the next one 55, because then that means this space from here to here is 10, while this space from here to here is 45. They need to be equally spaced. So what you could do is just decide on how much you're going to call each of these grid marks and then just approximate on the point. So I'm going to call them 50 each. I'm going to call this 50, 100, 150, 200, 250, 300, and that'll take me as high as I need to go as far as these Y values right here. So now I'm going to have to approximate when I go to plot my points, just because I'm not using the exact numbers from the table. So when I go to plot 0, 10, that's going to be approximately right there, a little bit above the x-axis, 0, and then up 10. I'm going to plot 555. It'll be 5, and then just a little hair above, and then 10, 100. It's going to be right there. And I'm going to go 15, 145. This is 150, so a little bit below that, keeping in mind that they have to line up anyway. This is a consistent jump of plus 45, plus 45, plus 45. Okay, then I'm going to go 2190, a little bit under the 200 mark. And I'm going to go 25, 235. That's going to be about right there. And then 3280 would be just a little bit below the 300 mark. And then you can connect them. Okay, and I'll just finish this off with the same things I did the last problem. Sorry, I'm running a couple minutes over. I'm going to do the slope and write the equation, just so you have a full review of what was in section 3.2 and 3.5. Okay, so you got to pick two pairs. I like to stay small, so I'm probably going to use the 0, 10 and the 555. I'll write those right here. 0, 10 and the 555, the second point down. Okay, this time I guess I'll go from bottom back up. So I'm supposed to be doing the Y's on the top, X's on the bottom. My Y's are 55 and 10. And my X's are moving in the same direction, 5 and 0. So this is going to be 45 over 5, which is still 9. The Y-intercept, because I want to write the equation as well. So the Y-intercept is the point on the Y-axis, which you can see right here in the graph is 0, 10, but you can also see it in the table. So 0, 10 is the Y-intercept. You're always looking for the point that has X as the has 0 as the X coordinate, but then this is the actual Y-intercept, the number in the Y position. So if you are finally asked to write the equation of a line, this is the slope-intercept formula, like I did for the last problem. You're going to be using you need the slope, you need the Y-intercept. So here it is 9 for my slope, I just got from the slope formula. And my Y-intercept is 10. Okay, and that completes section 3.7 as well. So that is the whole chapter. Again, next week I'll be signed in right here, waiting for you if you have any questions and ready to take your questions. Have a beautiful week, beautiful weekend. No official attendance required next week. Next week is your testing week. Remember to get that test done by Sunday, as well as the portfolio. Okay, everyone, have a beautiful day. Bye-bye.